So the matrix A, which is given by row 1, 2, 3, row 4, 5, 6, has order 2 by 3. And remember, order is just our fancy word for size. So when we say order 2 by 3, we really mean its size, and that's 2 rows and 3 columns in this case. So for matrix representations, we will always use a capital letter to represent a matrix. So when we're talking about matrix A, we will represent it by capital A. If we then want to talk about the elements or the things that are inside of matrix A, we will reference them by the same letter, but we will use a lowercase to represent that we're talking about elements on the inside. We will address elements inside a matrix by giving you their row and their column. So, for example, using our matrix A here, A21 tells us we are looking for the element in matrix A that is in row 2 and column 1. So if I go to row 2, column 1, that's right here, and I see that the element that is in the second row, first column, is 4. So A21 is equal to 4. So if we look at our next example, it says, well, what is A13? Well, it's asking me, well, what's in row 1, column 3? So row 1, column 3 is going to be equal to 3. And our last one is row 3, 2. So row 3, column 2. And you say, hey, wait a second. How many rows does matrix A have? It only has 2. So is there any elements in row 3? No, because it does not exist. A has only 2 rows. So we need to be a little bit careful when we're doing this. The second thing I want to note is when a matrix has less than 9 or less rows and 9 or less columns, we'll notice we did not put a comma between the 3 and the 2, or the 1 and the 3. If a matrix A has 10 or more rows or columns, we will use a comma to separate rows and columns in the subscript. So, for instance, if I had A11, 3, so 11, comma 3, this would be what's in row 11, column 3. And so notice, if we have more than 9 rows or columns, if I just write 1, 1, 3, that's ambiguous, right, without that comma? Because that could be row 1, column 13, row 11, column 3, right? And without that comma, we can't tell. So the convention is if we have 9 or less rows or columns, we don't need the comma. The first one's the row, the second one's the column. For a matrix that has more than 10 rows or more than 10 or more columns, we have to put the comma to separate them. All right. So the first thing we are going to define is matrix equality. So two matrices are equal if and only if, one, they have the same order, and remember order just means size, and two, all of their corresponding entries are equal. So in symbols, that means matrix A equals matrix B if and only if A sub ij is equal to B sub ij for all I and j. So let's talk a little bit about what this means. So A sub ij is the entry in row I, column j. And B sub ij is the entry in row I, column j, right? So when we write this notation, A sub ij equals B sub ij for all I and j, it says for every row and column, all of the entries are equal. So matrix equality means what you think it means. It says two matrices are equal if they have the same size and all of the stuff on the inside is exactly the same. So whatever's in row 2, column 2 of matrix A has to be the same as what's in row 2, column 2 of matrix B. What's in row 3, column 1 has to be the same as what's in row 3, column 1. All right, let's look at a couple of examples. So example 2 says, does A equal to B? So by definition, two matrices are equal if they have the same size and all of their entries are equal. Well, when we look at A and B, matrix A only has entries 2 and 3. Matrix B has entries 2 and 3. But the two matrices are not equal because they do not have the same size. So the size or the order of matrix A is, it has 2 rows and 1 column. So 2 rows, 1 column. The order of matrix B is 1 row, 2 columns. So they have different sizes. So A cannot equal matrix B. So it doesn't matter if even if the stuff on the inside is the same, if they don't have the same size or the same order, the two matrices cannot be equal. So if we look at example B, matrix A and matrix B here, they are the same. So A does equal B. Because if I check, A11 is equal to 3, which is equal to B11. A21 is equal to -2, which is the same as B21. And A31 is equal to 7, which is the same as B31. So the entries in the same location and in each matrix are the same. So what's in row 1, column 1 of matrix A is the same as what's in row 1, column 1 of matrix. So our next example says find x and y such that matrix A is equal to matrix B if A equals 3, 2x plus y, and 10, and B equals 3, negative 2, and x minus 2y. So we want to find x and y so that matrix A does equal matrix B. And if we look in row 1, column 1, both matrices have a 3. In row 2, column 1, matrix A has 2x plus y. In matrix B, row 2, column 1 is negative 2. So for these two matrices to be equal, 2x plus y has to equal to negative 2. Similarly, if I look in row 3, column 1 in matrix A, I get 10, and row 3, column 1 of matrix B, I get x minus 2y. So for these two matrices to be equal, I would have to have 10 is equal to x minus 2y. So if I multiply equation 1 by 2, it's going to give me negative 4. This should have been 4x plus 2y. That gives me 6 is equal to 5x. Divide by 5, and I get x is 6/5. And then I put that back in. 2 times 6 over 5 plus y equals negative 2. Gives me 12 over 5 plus y equals negative 2.
Professor, I have a question.
Yes. Plug it back in. We minus 12 over 5. And we minus 12 over 5, and we get y equals. So negative 2 take away 12 over 5, make it a fraction over 1. Multiply by 5 over 5. We would get negative 10. Take away 12 over 5, so negative 22 over 5. And that would be our x and our y that would make those two things equal. And this time that's the right numbers. So the basic idea is that two matrices are equal if and only if their corresponding entries are equal. All right. So in row 1, column 2, we have x minus y, and x minus y has to be the same as 6. And in row 2, column 1, we have x plus y, and that's going to have to be the same as negative 6. This time, to solve, we don't have to do anything. We can actually just add the two equations together. And when we do so, we get 2x is equal to 0. So we divide by 2, divide by 2. We get that x has to be 0. Well, if x has to be 0, then putting it into the green equation, 0 plus y has to be negative 6. So then y is negative 6. And we could check that to see if we get what we're supposed to. So 0 plus negative 6 is negative 6, and 0 minus a minus 6 is positive 6. So indeed, we have our two solutions. X is 0, and y is negative 6. All right. We're going to talk about a couple of special matrices to get started. And we've seen these ones before. So a matrix that has only one row is called a row matrix or a row vector. And you'll hear the word vector used when it consists of only one row or one column. A matrix with a single column is called a column matrix or a column vector. The other special type of matrix is a matrix with the same number of rows and the same number of columns is called a square matrix. So we'll have occasion to use both row and column matrices or vectors in some examples coming up. So to add or subtract matrices, the following must be true. They must have the same size. If they have different sizes, their sum is undefined. To add them, we add or subtract their corresponding entries. So in symbols, the matrix A plus the matrix B is equal to Aij plus Bij. That is, we add the things that are in the same row and in the same column. Well, let's take a look at our next example. So example 3 says simplify if possible. So in example A, we want to add the column vectors 2, 1 and 4, -1. So notice they are both 2 rows and 1 column. So the size is a 2 by 1 and a 2 by 1. And when we add them together, we will add their corresponding entries. So then that would be 6, and 1 plus -1 is 0. We end up with the new matrix 6, 0, which also has size 2 by 1. So a couple of observations. It says to add matrices, they have to have the same size. When we add two matrices, the result will always be a matrix that had the same size as the two add-ins. So matrix addition or subtraction, for that matter, will never change the size of a matrix. So we had 2 rows, 1 column, 2 rows, 1 column. Our sum had 2 rows and 1 column. So now if we look at our next example, example B, we have a column vector and we have a column matrix. So once again, we have a 2 by 1, but here we have a 1 by 2. So the difference is undefined. They don't have the same size. So if we ever try to add two matrices or vectors that don't have the same size, we're done and it's undefined. All right, so this matrix addition, or subtraction in this case, will work because they're both 2 by 2 matrices. So we're going to have 2 minus a minus 4. We're going to have 3 minus a minus 1. We are going to have 4 minus 2. And lastly, we're going to have 5 minus 5. And then we simplify. Minus minus is plus. 2 plus 4 is 6. 3 plus 1 is 4. 4 take away 2 is 2, and 5 take away 5 is 0. So we end up with the matrix with row 6, 4, and row 2, 2, and 0. All right. So the first thing we want to talk about with regards to matrix algebra is the idea of an additive inverse of a matrix. So when we have numbers, what's the additive inverse of the number 5? Well, it's -5, because 5 plus -5 gives us 0. So to undo adding 5, we do its opposite, which is to subtract 5. Well, we're going to generalize that to matrices. To obtain the additive inverse of a matrix, we replace each entry with its opposite. So to find negative A, so we want to find negative A if A is equal to 2, negative 1, 3, and row 2 is negative 3, 1, and 4, and then compute A plus negative A. Well, if this is A, then negative A is going to be a matrix of the same size, but we're going to replace each entry with its opposite. So the opposite of positive 2 is negative 2. The opposite of negative 1 is positive 1. The opposite of positive 3 is negative 3. The opposite of negative 3 is positive 3. The opposite of positive 1 is negative 1. And the opposite of positive 4 is negative 4. So our matrix negative A is the matrix negative 2, 1, negative 3, and 3, negative 1, and 4. So now we want to compute A plus negative A. Well, that's going to be our original matrix, 2, negative 1, 3, negative 3, 1, and 4, plus the matrix we just found, negative A, negative 2, 1, negative 3, 3, negative 1, and negative 4. So the sum is going to be a matrix of the same size. So in row 1, column 1, we have 2 plus negative 2, which is going to be 0. In row 1, column 2, we're going to have negative 1 plus 1, which is also 0. And in row 1, column 3, we're going to have 3 plus negative 3, which is also 0. In fact, every entry in the sum is going to be 0. Because to construct the matrix negative A, every element became its additive inverse. And A plus negative A, or x plus negative x, for every x is going to be 0. That's our property of additive inverse from real numbers. So the matrix that we just saw with zeros for all of its entries has a special name, and it's called the zero matrix. So the zero matrix, there is not a zero matrix. There is a zero matrix for every size of matrix, because by definition, to be a zero matrix, it's going to have to be all zeros. So the 1 by 1 matrix would just be 0. The 2 by 2 matrix would be 0, 0, 0, 0. And the 3 by 4 matrix would be 3 rows of all zeros with 4 columns. So the zero matrix behaves like the number 0 does in the real numbers. So what I mean by that is that for any matrix A, A plus the zero matrix is going to be A. Just like if you take any real number, if I take the number 3 and I add 0 to it, what do I get? 3. If I take the number x and I add 0 to it, what do I get? X. The zero matrix is going to behave exactly like the number 0. The next thing we want to talk about is called scalar multiplication. So we're going to define this multiplication as between a number and a matrix, or a number and a vector. So the scalar product of a number k and the matrix A, denoted k times A, is obtained by multiplying each entry of the matrix A by the number k. the number k is called a scalar as opposed to a matrix or a vector. So we want to use the matrix A equals -5, 1, and row 2 is 0, 2 to find 3 times A and -1 times A. So 3 times A is going to be 3 times the matrix, -5, 1, 0, and 2. And by definition, it says we multiply every entry in the matrix by the scalar. So it's going to be 3 times -5, 3 times 1, 3 times 0, and 3 times 2. So that's going to give us -15, 3, 0, and 6. So 3 times A would give us the matrix with row 1, -15 and 3, and row 2, 0, 0, 6. -1 times A says, I'm not going to write it out quite as verbosely, we just multiply every entry by -1. So -5 times -1 is 5. -1 times +1 is -1. -1 times 0 is going to be 0. And -1 times 2 is -2. So -1 times A is the matrix 5, -1, 0, and -2. It's worth noting the matrix -1 times A is the same as what we were just doing up here. The opposite or additive inverse. And so that is also true for real numbers. If I wanted to find the opposite of the number 5, or its additive inverse, what would I do? Change its sign, which is the same as saying I multiply by -1. So if I multiply 5 by -1, I get -5, which is the additive inverse of 5. That same property holds for matrices. If you want its additive inverse, just multiply it by -1. All right. So here is a summary of the properties of matrices, at least for the operations that we've talked about so far. So if A, B, and C are any m by n matrix, and O is the 0 matrix, then the following are true. So matrix addition is associative. So the order we group them in doesn't matter. Matrix addition is commutative, so 3 plus 4 is the same as 4 plus 3. If we add the 0 matrix to something, we get the same matrix, so our additive identity holds. If we add the negative, or the opposite, of a matrix to itself, we get the 0 matrix. Scalar multiplication distributes over matrix addition, and scalar addition distributes over matrix multiplication. So C times A plus B is CA plus CB. And if I have C plus D times A, it's the same as C times A plus D times A. And finally, scalar multiplicative identity. 1 times a matrix A gives us the matrix A. And the scalar 0 times the matrix A will always give us the 0 matrix, because 0 times any entry will give us 0. So all of our entries would be 0, and we would get the 0 matrix. So we inherit, at least for addition and scalar multiplication, all of the normal or usual properties that we are accustomed to. Okay. Let's take a look at example 7. So we're asked to solve for x. And we're given the equation 2 times x plus the matrix 4, negative 3, 1, 6 is equal to 1, negative 5, negative 5, 2. So at first glance you might think, okay, well, what do I do? Well, this is exactly the same. If I asked you to solve this equation, 2x plus 4 equals 1, what would you do? Well, you'd subtract the 4 over to the other side and then get x by itself. The exact same thing is going to happen with matrices. So I'm going to minus the matrix 4, negative 3, 1, 6 from both sides. The fundamental rule of equation says if I do it to one side, I have to do the same thing to the other side. So on the left side, they reduce out, and I have 2x is equal to, well, 1 minus 1 is going to give me 0. Negative 5 minus, I wrote the wrong matrix. I'm like, that shouldn't be all zeros. 4, negative 3, 1, and 6. Let's try that again. So 1 minus 4 gives me negative 3. Negative 5 minus a minus 3. So minus minus makes it plus. So negative 5 plus 3 is negative 2. Negative 5 minus 1 is negative 6. And 2 minus 6 gives me negative 4. So now I need to multiply both sides of this equation by 1/2. Because 2 times 1/2 gives us 1 times x, which is just x. So let's formally write that out. So I get 1 times x equals, and then I get negative 3 over 2, negative 1, negative 3, and negative 2. But 1 times x is just x, so I get x is this matrix. So the solution to that equation is the matrix negative 3/2, negative 1, negative 3, and negative 2. And just like with regular algebra, if I take this back up here and plug it in for x and simplify, I'm going to get the matrix on the other side, right? So other than that they look different and we're using matrices instead of numbers, so far they behave just like the same algebra that we've learned, right? We're using matrices instead of numbers, but everything works out the same, which is kind of cool. Let's take a look at our next example. So Spacely Sprockets manufactures 3 types of sprockets at 2 different plants. The table below lists each type of sprocket produced at each plant in November. So the Orbit City plant produces 150 taper locks, 120 multiple strand, and 100 double pitch. The Lunar City plant, missing a T there, makes 180 taper lock, 90 multiple strand, and 140 double pitch. So we want to write a 2x3 matrix A that represents the information in the table. So our matrix A, each row is going to tell us about the production at each plant. So we would have 150, 120, 100, and our second row would be 180, 90, and 140. So B says the manufacturer increases production in December by 20%. Find a matrix M that represents the increased production figures. So, for B, if we increased our production by 20%, that means we're going to make all of the things we made before plus 20% more, right? So what is 120%? So it's 100% plus 20%. So what is 120% as a decimal? 1.2. So this is our 20% increase. So then our matrix M would be 1.2 times our matrix A, right? So that's going to be 1.2 times 150, 1.2 times 120, 1.2 times 100, 1.2 times 180, 1.2 times 90, and 1.2 times 140. So 1.2 times 150 is 180. 1.2 times 120 is going to be, what, 120 plus 24, so 144. 1.2 times 100 is 120. 1.2 times 180 is 180 plus 36, so 216. 1.2 times 90 is going to be 90 plus 18, so 108. And 1.2 times 140 is 140 plus 28, so we get 168. So our matrix M represents this. So 180, 144, 120, 216, 108, and 168. So now C says find the matrix A plus M, and what does it represent? Well, if we add A and M, we're going to get 330 plus 264. And 220. 216 and 180 is going to be 396. 108 and 190 is 198. And 140 and 168 is going to be 208. So there's A plus M, and what does it represent? Well, what did A represent? A represented the production in November. And what did M represent? The production in December. So A plus M is the total production in November and December. Because M represented the increased production for December. When we add the two matrices together, we get the total production. So it's worth noting we can do a lot of this stuff in a much more abstract way. So M was equal to 1.2 times A, right? So A plus M was really the same as A plus 1.2 times A. Well, we could factor out our common factor of A, and that's 1 plus 1.2 times A, which is really just 2.2A. Or if you want to think of it this way, we could put the coefficient in front. If we collected our like terms, what's A plus 1.2A? 2.2A, right? So we could have skipped right to the answer by just multiplying the matrix A by 2.2, right? So these abstract algebraic symbols do have a lot of power, where we can compute things point by point like we did, but the true application is going to start coming in when we do things like this, where we can treat them as algebraic objects. And just keep doing some things like this to make our calculations simpler. All right. Last thing we want to talk about in 5.1 is this. So another definition, we want to define a new operation on a matrix. And that operation is called transposition. So if matrix A is an m by n matrix, then its transpose is the n by m matrix obtained by writing the columns as rows and the rows as columns. For example, row 1 would become the new column 1, and row 2 would become the new column 2, and row I would become the new column I. So if A is an m by n matrix, so it would have m rows and n columns, its transpose would then have n rows and m columns. So if we have our two matrices, matrix A and matrix B, let's go ahead and calculate these. So A transpose, our row 1 would become our new column 1. So the length of row 1 is 4. So our new column 1 is going to have 4 things in it. It would be 1, 2, 3, 4. Row 2 would become our new column 2. So 5, 6, 7, 8. So A transpose, we basically turn all the rows into columns. That's all we're doing. Okay. So now, let's go to B. So B says find A plus B in parentheses transpose. So A plus B parentheses transpose, by the order of operations, we need to do A plus B first. So we need to add matrix A to matrix B. So we have 1, 2, 3, 4, 5, 6, 7, 8, and we want to add that to 2, 4, 6, 8. 1, 3, 5, 7. And then we're going to take the transpose. So we add them up. So we get 3, 6, 9, and 12. And we get 6, 9, 12, and 15. Then if we transpose that, we're going to end up with our new matrix. If I made them square, I should make them all square. Our new matrix is going to be 3, 6, 9, and 12, and 6, 9, 12, and 15. So A plus B transpose is this. Part C says find A transpose plus B transpose. So A transpose plus B transpose is going to be, we transpose matrix A, we get 1, 2, 3, 4, 5, 6, 7, 8, plus we transpose matrix B, we get 2, 4, 6, 8, 1, 3, 5, and 7. So now we add the corresponding entries, and we get 3, 2 plus 4 is 6, 3 plus 6 is 9, 4 plus 8 is 12, 5 and 1 is 6, 6 and 3 is 9, 7 and 5 is 12, and 8 and 7 is 15. So we end up with the same answer that we got for B. So note, and this turns out to always be true, that A plus B, adding first and then transposing, will always give you the same answer as if you transpose first and then add. So the transpose doesn't care if we do arithmetic first and then transpose. Okay. D says find B transpose, transpose. So before we work that out, what do we think B transpose, transpose should equal? If you make all the rows columns, and then you turn all the rows into columns again, what's going to happen? Well, let's see. So B transpose is going to be, we transpose our matrix B, we get 2, 4, 6, 8, 1, 3, 5, 7. But now we need to transpose it again, so all of our rows are going to become columns. So my new first column is going to be 2, 1. My second column is going to be 4, 3. My third column is going to be 6, 5. And my fourth column is going to be 8 and 7. Oh, wait a minute. That is just back to the original matrix B. So we note that for simplification purposes, B transpose transpose is going to be the same as matrix